Gentlemen, welcome back. I hope you're all having a great day because I'm going to make it much worse for some of you. We're going to cram probably 2 years of electrical theory classes into the next
56 minutes.
This certainly isn't everything that you need to know to take your NETA 2 or your NICET 2 or 3 or 4 exam, but I want to take a minute to look specifically at the math. Not only do you need to know how to use these formulas for the tests to pass the next certification level, but having understanding of these formulas and what they mean and how we apply them is going to make you a better technician in the field. If you're new here, welcome. I make tutorial videos specifically covering the industry of electrical testing, from low voltage circuit breakers and cables all the way up to high voltage substations and protection relays and fun stuff like that. I am both a NETA 4 and a NICET EPT level 4 certified technician. I've been in the industry for about 11 years, and I've gotten to play with some of the biggest and most expensive power delivery equipment on the planet. All that, and I was a C student as a kid, and I didn't go to college. If I can figure out how to do a little bit of math to pass the exams and, chase a raise, so can you. That's what I'm here to hopefully shed some light on today. There are some prerequisites that I'm going to skip here. You need to have a really firm grasp of high school level algebra and maybe a rudimentary knowledge of trigonometry. I don't want to scare anybody. By trigonometry, I really just mean know when to punch the sine and cosine button on your calculator. Nothing much more extravagant than that, but we are going to go through a little bit of the theory today. If high school algebra is looking pretty fuzzy in hindsight, there's a link in the description for Khan Academy. It's like an online school to brush up on all the stuff that you slept through the first time. And another great resource that I do want to mention for learning your electrical basics is going to be allaboutcircuits.com. I love them. They cover things in way more depth than I can get into in a video like this. Neither of them are partners of the channel or sponsors. I just think they're really, really good tools to keep around. And if you need to brush up on something, they're free online resources. They're fantastic. I want to take a quick moment to mention that all of my videos here on YouTube or wherever they're going to be free for everyone forever. I'm never going to charge a fee for one of my tutorials. I'm really passionate about sharing knowledge and lowering the barrier to entry for guys getting into the trades. So far, all of the crap that I've bought for the channel has come out of my pocket, which admittedly I'm extremely happy about, and I'm extremely privileged to be able to do that, but it certainly adds up. If you've got disposable income and sort of share my vision, consider becoming a channel member by hitting the join button down below. You can check out the neat little perks that I give everybody. If it's not in the cards for you right now, I totally understand. It's no pressure. Just hit the like and subscribe, and I will keep making these tutorials. I do want to mention if you are studying pretty heavily for your exam, you'll want to do additional practice outside of this video. Like going through the formulas is nice. It's critical, but you'll need to actually do your own practice problems to apply it yourself. It really helps it sink in if you're studying. Both NETA and NICET give you a formula cheat sheet to use during the exam. We're going to cover all of those, the basics of Ohm's law, and we'll get into a few other things that I think will really help, especially if you don't have a background in, electrical engineering or being a field service technician for something else. I'll also walk through an example problem for each formula and each thing that we're going to talk about. The first thing I want to talk about is called engineering notation. You're likely familiar with scientific notation from chemistry class, but the way that it's taught in high school kind of sucks. You scale really big numbers and really small numbers into a range between 1 and 10. The significant digits are followed by times 10 to a power. So big numbers get a positive power, showing how many times the decimal point has to move to the right. Small numbers get a negative power, showing how many times the decimal point has to move to the left. In electrical engineering, field testing, and a lot of related fields, we use engineering notation instead because the numbers that we talk about on a daily basis are either really, really big or really, really small. It works exactly the same way as scientific notation, except instead of a scale between 1 and 10, we use a scale between 1 and 1,000. This means that you'll only have powers of 10 in multiples of 3. So 6 times 10 to the third, or 196 times 10 to the minus 6. Those are the sort of numbers that we're looking at. Now, I know a lot of techs are like, No, what the hell are you talking about? We don't use engineering notation. I've never seen this before in my life, you nerd. But you do. And hear me out. We use it conversationally using cool words for each scale instead of saying, 10 to the ninth or something like that. Every number we look at obviously has a base unit, whether it's a volt, an ohm, a coulomb, or a henry. If it's 20,000 volts, we scale it down and call it 20 kilovolts. It's scaled the same way. It's scaled in engineering notation. We just use the word kilo instead of 1,000. 99% of what we deal with is going to be between like 1 in a trillion or about 1 in a trillionth. So I want to go over really quickly the scales for those. So the scalar names that you need to know going up, so getting larger, you have your base unit, kilo, which means 1,000 or 10 to the third, mega, which is millions or 10 to the 6, giga is billions or 10 to the ninth, and then tera is trillions. 1 tera ohm is 1 trillion ohms. And in testing, that is something that we deal with on a fairly regular basis, and you might see tera ohm come up somewhere on your test. The scale going down is really similar. We just go down in steps of minus 10 to the minus 3. So going down, we start at your base unit, so volts, ohms, henries, whatever it is. Divide that by 1,000, you've got milliohms, millivolts. Milli is the scalar word that we use, which is thousandths. Micro is millionths, or 10 to the minus 6. Nano is billionths, so you might see a nanofarad. Well, that's a billionth, 1 billionth of a farad, and that'll be 10 to the ninth. And then pico is a trillionth. Not a whole lot of stuff that we're going to do that is in picofarads, things like that. It's just worth being aware of. It's definitely a scalar name that I would just have memorized just in case. Once you've had a few years in the field using these on a day-to-day basis, conversing with people and writing reports and things like that, it becomes second nature and it's really not that difficult to keep up with. But when you're first starting out, it is really, really odd, especially if you hear somebody sort of mixing those units and saying, oh, it's 1,500 mega ohms. Well, is that a giga ohm or is that a kilo ohm? There are a ton of good mnemonic devices out there that you can look up and they can help you remember it. The one that I always remember from years ago is thick goth mommies kill you, massage my nipple please. The only odd thing I want to talk about is how you write some of these scaled numbers on your test sheets. If we use volts as our base unit, say start at 10 trillion and divide by 1,000 each time, they'll look like this. So 10 teravolts would look like this. Note that both the T in tera and the V for volt are both capitalized. 10 gigavolts, G is capital. 10 megavolts. Pay attention to the capital M. You'll see why in just a second. 10 kV or 10 kilovolts. You'll hear things like that all the time. 35 kV, 15 kV. The K is lowercase. It is important, but not as important as the M. The base unit, you won't see a scalar unit, so we'll just go with 10 volts. The next one down is millivolts, which is thousandths of a volt. You'll see it like this. It's a lowercase m because we've already used the uppercase M. The next one down is microvolts. So 10 microvolts would look like this. We already used M twice, so we had to come up with something else. So we use the Greek letter mu to be short for micro. It looks like a little fucked up U. If you're filling out a test sheet on an iPad or something like that and you can't find the Greek mu button, you can just write the letter U as that scalar and people will know what you're talking about. The next step down from that is going to be nano. So 10 nanovolts would be how we write that, and that's a lowercase n. And then the final one, the smallest one, is going to be lowercase p, 10 picovolts. The first thing that we need to talk about is Ohm's law. Ohm's law on most like real basic circuits or DC circuits can be expressed very simply as V equals I times R. We can permutate that a couple different ways. I equals V divided by R, and then R equals V over I. Alternatively, an easy way to remember that is to draw it like this. V equals IR. So the V is always on top if it's getting divided, and then it also equals I times R. It's just an easy way to sort of draw it out and remember it. It really only works for like perfectly resistive circuits, really simple circuits, or DC circuits. The first kind of example that I want to roll into here, on a DC circuit, basically anytime we do a circuit analysis on that, we're going to assume that our DC supply is like a battery, so we draw it like a battery. In this case, I don't know what my voltage is, but I do know that I've got, say, 1 amp of current flowing through a resistor that has a resistance of 5 ohm. If I have to solve for V, my formula here is V equals I times R. I can plug in 1 amp for that, 1 amp times 5 ohms. Well, that's just 1 times 5. So my voltage equals 5 volts. I hope that's not new for anybody. I mean, if we're at this point, this is as bare bones, as basic as it gets, but I do want to run through a couple of the permutations of Ohm's law real quick. So next up, I mean, if we look at another example that's very similar, we just go through another permutation of it. Say I give you 10 volts on this, on this battery, and I have a 5 ohm resistor. How much current is there? So I need to solve for I. My formula to solve for I on a DC circuit or a very basic circuit is going to be I equals V over R. So in this case, that's going to be 10 over 5. I equals 2, and we always have to use we have to show our units here. So I equals 2 amps. The last one of these that I want to run through, how do we solve for a resistance if I know my voltage and my current? So say I've got a 24 volt battery here. So I've got an ammeter shown here that says I've got 12 amps. I've got a voltage of 24 volts. And then my resistance is R equals V over I. In this case, voltage is 24. We're dividing that by 12 amps. So R equals 2 ohms. Never forget your units here. Part of Ohm's law is also this power equation. We have to be able to solve for power. Pretty simple. Again, when we're talking about DC circuits, DC essentially has a power factor of 100%. This is always true for DC, and it's sometimes true for AC, but we'll get into that more here in a second. So given a example where I know the voltage and the current, but I need to solve for one of the formulas that I don't have yet, right? Like I've got this one down. I know V equals I times R, and I know power equals I times V. Well, how do I solve for this other one? I need to get the solution to the current as well. So this is going to be power equals my current is V over R times my voltage. P equals 12 volts over 2 ohms times 12 volts, which we can simplify down to being 6 times 12, which we can then further simplify down to being power equals 36 watts. You have to fill in the blanks for the variables that we're missing.
I'm outside now. I've been editing this for hours and came to the realization that I did a really crappy job explaining some of it and I need some fresh air. So here I am. When you look at any DC voltage, whether it's a 9-volt battery or a 24-volt power supply, it makes intuitive sense that what you measure is the potential energy pushing current through that whole circuit. The units of voltage, current, and resistance are mutually defined by the amount of heat or chemical energy consumed in a given circuit. AC circuits are fucking weird, though. If you take a plot of alternating current or AC voltage over time, you get a sinusoidal waveform. It makes more sense when you remember that the grid, which is the biggest AC circuit imaginable, is it's powered by a bunch of generators, which are big-ass magnets spinning in a circle. You can plot a point on a spinning circle over time as a sine wave. The electrons and the wires aren't headed in a single direction. They're oscillating back in place 50 or 60 times a second. So how on earth do you actually measure that? If I simply take a measurement of the voltage at the peak of that wave, which we can do with something like an oscilloscope, this value is substantially different than what you would expect if we plug in, Ohm's law and work back to a known amount of energy consumed. Smart people a really long time ago figured out that measuring voltage this way is just wrong, and it doesn't relate to similar DC circuits or any other physical phenomenon. So can we use the average voltage over time? Well, also no, because half of the time the voltage is negative, right? So if it's dipping below that 0 volt line, if you take the average of all these measurements, it would just be 0. And that's not really useful either. So we don't actually take the average. What we really want is something called the RMS voltage. This is similar to calculating the area under the curve of the waveform. That's not like technically true. I'm sure some engineers are going to spout off in the comments about how that's wrong, but conceptually it's more similar to what we actually want. It's the useful energy available in a circuit from that applied voltage. You could calculate the RMS the hard way with all of this bullshit. A bunch of nerds in top hats over 100 years ago determined that a really good approximation of the useful electrical potential energy in a circuit, which we call RMS voltage, is the peak voltage of that sine wave divided by the square root of 2. That's what RMS stands for, root mean squared. If you punch that into your calculator, the square root of 2 is like 1.414. Given an example here, 10 volts RMS would have a peak of 10 times the square root of 2, or about 14.14 volts peak. Going the other way, say I have 97.6 volts peak, I can divide that by the square root of 2 and get 69 volts RMS. Nice. Two key things to remember. The peak voltage is always higher than the RMS voltage, so you can kind of dummy check yourself when you're on your test. And number two, almost every time you see an AC voltage, current, or watts on a multimeter, a relay, or a breaker, that's in RMS quantity, not a peak quantity. If you see on an oscillograph, or like an event analysis on a relay, something similar to that, that might show you the peak quantity, so you need to know the difference and how to get back and forth between the two. The other oddity about measuring AC voltage is regarding three-phase systems. You need a firm grasp of three-phase power for this line of work, but this video is way too long already. So here's a link below for an amazing video by the Engineering Mindset that's a pretty good job of explaining that if you need to get caught up. What I do want to talk about specifically is phase to neutral or phase to ground voltage versus a phase to phase voltage measurement. We often use Y-connected systems where we have 3 phases and a neutral wire that we can have either 3-phase loads like motors and transformers connected to, or we can connect individual single-phase loads between the phase and the neutral. If I take a voltage measurement from one hot phase to ground or to neutral, in the example here, I'll have 277 volts. But if I take a measurement between A phase and B phase, I'll see 480 volts, which is more voltage. The ratio between the phase to neutral and a phase to phase voltage in this case is multiplied by the square root of 3. Due to the phase angle offset between their sine waves, as they're a third of a full revolution away from each other. If I give you a phase to phase voltage of 208 volts, you can divide that by the square root of 3 and get the phase to neutral voltage of 120 volts. Anytime you see a transformer or a motor nameplate that has 2 numbers with a slash between them, the bigger number is the phase to phase and the smaller one is the phase to neutral voltage. Some 3-phase systems are connected in what we call a delta configuration because the phasor diagram looks like a triangle or the Greek letter delta. It's really creative. On a delta system, we can only have loads that are connected between 2 or 3 phases, 3 of the hot lines. The voltage for a delta system will only have one number, and it's the phase-to-phase voltage. So it's the phase between A and B, B and C, or C and A.
As we dig into AC circuit analysis and impedance and things like that, it's sort of the difference between AC and DC gets a little bit more stark. Number one, the power factor for DC is always 100%. Every load in a DC system can be expressed as a resistance. It can be expressed as power consumed by a resistor, whether it's an LED or a resistor or a motor or whatever. The amount of current through the system is going to be the amount of current, and it can be expressed as a resistance. It can be expressed as a resistive load. In AC, because things get significantly more complicated, like the phase angle shift between my current and my voltage affects our power factor, and power factor affects a lot of other things, and different types of load affect how the current and voltage relate to each other. It's really, really important that we have units that make sense for that. And for a lot of the stuff that we're going to discuss moving forward, our equation for Ohm's law changes a little bit when we're talking about AC. So on a DC circuit, V equals I times R, right? Because R can express any kind of load that we're going to have. On an AC circuit, we use V equals I times Z. Now, Z is it's a compound unit of a bunch of other things. That is impedance. Z means impedance. On a DC system, if I have something like an inductor, which is basically just a coil of wire, so a transformer winding, a motor winding, something like that, current will just flow through. It really doesn't care that there's a winding there at all. And a capacitor, once, during steady state, current doesn't flow through it anymore. It is stopped by this capacitor. Once the capacitor is fully charged, it acts like an open circuit, like an infinite resistance. On AC, what this does, current still flows through it, but it creates sort of a magnetic field and pushes the current all over the place. And on a capacitive circuit, the current kind of charges up and kind of flows through it and kind of does all these goofy things. Like I said, it mushes the phase angles around. So we're going to talk about some of these equations and some of the permutations of this Ohm's law in an AC circuit, V equals I times Z. In AC systems, the way that the capacitances or the impedances interact with the rest of the AC system, we have to describe with what's called reactance. Anytime you see X is the sort of the symbol for reactance. A couple examples of that you'll see pretty often. X of C, so a subscript C, X of C is the capacitive reactance. X of L, you'll see this pretty frequently, inductive reactance, so the reactance of an inductor. One that you'll almost never see is this one. So X of R, or I guess it's a big R, the resistive reactance. We don't talk about resistive reactance because a true resistor doesn't push or pull the voltage or the current ahead of one another. Anytime you have a resistive load, resistors by themselves have a 100% power factor. So X of R always just equals resistance. So we very, very seldom see X of R explained. I just want to mention that in case you get curious. We've got this fun little mnemonic called Eli the Iceman. I do want to take a quick shout out to this mnemonic. L for inductance in an inductive circuit, or anytime there is an inductor, the voltage leads, voltage will be in red, the voltage leads our current in an inductive circuit. On a capacitive circuit, so ICE, current leads the voltage. There is some lag, there's a phase angle shift, so the phase is pushed backwards with respect to time. Okay, so let's talk specifically about inductive reactance and how we solve this. Inductive reactance is, again, you can kind of think of it as like a sister of resistance, but it works differently because inductors, things like coils of wire, motor or generator windings or reactors, they do consume energy, but they also impede the flow of current by storing energy in a magnetic field. You don't need to know most of the math to describe how current is stored inside, a magnetic field. So if I've got a coil of wire here, current passing through it, I've got like a magnetic field around it that can push and pull electrons through other windings, or it can push and pull a motor, rotor, things like that. For most of what we're talking about, when it comes to NETA testing and specifically taking the NETA exams, we don't need to know all the engineering fun stuff about how that physically works, but we do need to be able to solve some equations regarding that. And to be able to convert from inductance to inductive reactance is a really important thing. So our formula for that is X of L equals 2 pi F for frequency times L, which is our inductance. So let's run through an example equation here and just solve for that. So our problem here, we have a 60 hertz waveform, a 60 hertz voltage source, and a 10 millihenry inductance. So whether this is a transformer winding or a coil of wire, whatever it is, it has an inductance of 10 millihenries. And we're going to solve for the inductive reactance. Again, our formula, X of L, 2 pi frequency times our inductance, is impacted by our frequency. Again, because it pushes or pulls the waveform back and forth. It pushes and pulls the current. Now 10 millihenries, in this case, we're just sort of dropping the units off. So that'll be 0.01. The easy thing to do once we have this all written out is we're just going to chunk this right into our calculator. 2 times pi times 60 times 0.01. And there we go. So our answer here is 3.769. So, and our unit for this, the unit that we're going to use anytime we're talking about reactance, is actually ohms. We have converted from a frequency in hertz and a inductance in millihenries to our inductive reactance in ohms. Now, they're not resistive ohms, so they're still different, and we'll get to how we combine those later, but it is shown in ohms. Okay, so the formula for X of C, or capacitive reactance, looks really familiar, except we're doing the inverse. So it's upside down. It's 1 divided by 2 pi times the frequency times the total capacitance. Again, it looks really familiar, but it's upside down because when I remember Eli the Iceman, we're pushing the current waveform forward of the voltage waveform. We're pushing it in the opposite direction as we were with impedance. It's just sort of an easy way to remember that they're backwards from each other. So here is an example where we're gonna solve for the capacitive reactance. What is our X of C in this case? Well, let's start with 1 over, because we know we're going to have to do that later, 2 times pi times our frequency, in this case is 400, times 600 microfarads. That will be 0.0006 farads. And we can drop the units off of here because we're converting it into something else. What I like to do, because I lose steps, especially if I'm doing this on a test, I tend to lose steps a lot when I'm doing stuff on a test. I'll solve all the stuff under the 1, and then I'll flip it over later. So we're gonna do 1 over 2 times pi times 400 times 0.0006. So we're getting 1 over 1.508, and then there's a button here, this 1 over x button. If we hit that, our answer here is X of C equals 0.6631 blah 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 ohms. And again, X of C, our capacitive reactance, we do draw in ohms. Okay, so here's our example, and I'll do the rest of this in blue so we're not writing over ourselves. I also wrote down these formulas over here, the X of C and X of L, because we're going to have to use those to convert our capacitance into an X of C and our inductance into an X of L. I need the capacitive reactance and the inductive reactance before I can do any other work to combine these into an impedance. Okay, so first step, just as we did before, our X of C, I need to solve for that by doing 1 over 2 pi times our frequency, in this case, is 60 hertz. That's all we need to know. And our capacitance is 0.009 farads. So we'll do that real quick. So we're going to go 2 times pi times 60 hertz times 0.0009 farads. We flip that whole thing upside down. Our X of C equals 2.947 ohms. We'll do the same thing for our X of L. X of L equals 2 pi times 60 hertz times 40 millifarads, 0.04, or sorry, 40 millihenries is 0.04 henries. So do the same thing, 2 times pi times 60 times 0.04. We get an answer of 15.08 ohms. X of L is 15.08 ohms in this circuit. So with all of that said, now that I've got my X of L and my X of C, I can start combining all of that into my impedance. So let's go Z equals the square root of 10 squared plus 2.947 minus 15.08 squared. Again, calculator, you're going to have a calculator during the test. It's pretty easy to plug and chug. 100 plus 2.947 minus 15.08 equals that. Squared is 147. And if I take the square root of 247.2, we find our answer Z, our impedance, is 15.722 ohms. So that is the total circuit impedance at 60 hertz. From here, just like any of our other Ohm's law equations, I can use that as essentially the resistance in our Ohm's law equation. So remember when I told you earlier, Ohm's law for AC is V equals I times Z. Well, if I know my Z and I know my voltage, I can solve for my current or my power or whatever else I want to do. In this case, we're going to solve I equals, V over Z, which means 120, in this case, 120 volts, over our impedance of 15.722 ohms. I would have a current of 22, gives us a result of 7.63 amps of current through this whole circuit. All right, hope that didn't scare anybody. We're gonna keep going. They get a little bit weirder. All right, that was a fucking mess, huh? So moving on, let's go to something easy. So how do we combine series resistors? That is an easy thing that I think is sort of intuitive. So if I've got a voltage source, and again with resistance, it doesn't matter if it's AC or DC. If I've got two resistors in series, so this is 10 ohms, and this one's going to be 30 ohms. Anytime I've got two resistors in series, or two resistances like our X of L in our previous example, two impedances, I guess, they both are going to resist the flow of current through the whole circuit. I would hope this is intuitive. Again, for some people that are just getting into this, it's kind of not. But if I've got two resistors that are connected end to end in series, they basically just add up and increase the total resistance for our circuit. The formula for R total in a series circuit, so RT, equals R1 plus R2 plus R3, and so on. So we just sum all of the resistances or impedances together. In this case, our R total equals 10 plus 30. Wow, go figure. Gave us an easy one today. So anytime that we've got resistors in parallel, because I've got more than one path that current can flow, intuitively, that means more current is flowing through the system. In this case, the overall resistance of the system, because I've got all of these other current paths, our overall resistance of the system is actually going to be lower than the smallest resistance in parallel. And the formula that we're going to use to solve this when I've got resistors in parallel, RT equals another one of those where we take the inverse, 1 over 60. This makes no sense written out, but once we start to solve it, you'll see what I'm talking about. 1 over 30 plus 1 over 9. If you wanted the actual formula for that, RT equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And then we take all of that, and then we either took it to the power of -1, or we, invert it 1 over that. However you want to draw that, it means the same thing. So let's get going. Let's plug and chug this one and see where we get. So RT equals, I know this is 1 over 1/60th, which is 0.1666 plus 1/30th. Oops, that's a third. 1/30th, 0.0333 plus 1/9. 1 divided by 9 is 0.111. Repeating. And all of those get added together, and then they get inverted. So 0.1666 plus 0.0333 plus 0.11111 equals 1 over 0.311. If you invert that, I get a total resistance of 3.215 ohms. And we can see that our total in this case is smaller than the smallest resistance, the smallest individual resistor in parallel, by a pretty good amount, right? Because I've got other paths for current to flow. In contrast, when we're looking at series resistors, our total is always going to be larger than our largest one. In parallel, our total resistance is going to be smaller than our smallest resistor in parallel. I hope that makes sense, because we're going to do the same thing for inductors and capacitors. How do we add series inductances? So fortunately, when we're adding series inductances, it's the same formula as adding series resistors. This one, fortunately, pretty straightforward, pretty logical, pretty common sense. LT in this case equals 60 plus 14. LT equals 74 millihenries. Hopefully that's not rocket science. We'll see in a second why it's easy. It's easy to screw up though. So parallel inductances, similar to resistors. LT equals 1 over L1 plus 1 over L2 plus 1 over L3, and so on, all inverted. So it's all 1 over that. It's all the inverse of the sum of the inverses. And I'm going to draw this real quick, and we'll get back. So in our example here, I want to solve for the total inductance. Again, inductance, not inductive impedance. We have to do that once we've summed them all. We're solving for the total inductances of multiple inductors in parallel. And I've got 10 millihenries, 20 millihenries, and 30 millihenry inductors, coils, windings, whatever. Just plug and chug into this formula. LT equals 1 over 1/10 plus 1/20th plus 1/30th. So we can just plug and chug that into here all at once. We're going to go 10 inverse plus 20 inverse plus 30 inverse equals, and we flop that whole thing over, and LT in this case is 5.454 millihenries. Got to make sure we get our units straight on that. Now, similarly to resistors in parallel, we'll see that this inductance is less than our smallest inductance. Just keep that in mind. When we're in parallel, we're adding, when we're in series, we're adding them. When we're in parallel, we are doing this giant inverted thing, and our result is going to be smaller than our smallest individual inductor. Okay, moving on. Let's do the same thing with capacitors. Now, capacitors, I don't like them. Series capacitances are backwards. It's the same formula that we remembered earlier for parallel voltage or parallel resistors and parallel inductors. It's the same thing. CT equals 1 over C1 plus 1 over C2 plus 1 over C3. I don't like it. It makes no sense that one of them is different than the other two, but you just gotta go with me. This is this is how it is. Okay, so here's our example equation. I've got 60 microfarads in series with 9 microfarads and 6 with 80 microfarads, and we need to combine them. Again, this is just sort of the inverted way that we do things for resistors and inductors, and the only way that I can remember that is because like current doesn't pass through them the same way that it does a resistor or an inductor. It's really like the field passing through. I don't know. If you can come up with a way to remember that, just remember that capacitors are basically upside down from the other ones. So we're going to do the same thing as before. CT in this case equals 1 over 1/60th plus 1/80th plus 1/9. And these are in microfarads. We can actually drop the units when we're doing it this way, because all the units are going to come out in the same, come out in the wash. It's all going to be the same. So we're going to plug and chug the same way that we did before. We're going to go 60 inverse plus 80 inverse plus 9 inverse. In this case, it is 7.128 microfarads. Definitely don't lose track of which units you were using when you put them all in. They all have to be in the same scale. Otherwise, you're going to get it totally wrong. And again, please remember that when we're combining things this way, when we're using this inverted equation, our answer should be smaller than our smallest individual capacitance. Similarly, to the other ones, like I said, capacitance is just this. We do the same math formulas. It's the same formulas as we have for resistors and inductors, except they're just inside out. It's going the other way. So when we're solving for the total capacitance of capacitors in parallel, we just add the total capacitances up, as opposed to them being in series where we've got this janky formula over here. So if we're going to solve this one, so I've got 100 microfarads, 20 microfarads, and 400 microfarads in parallel. Thanks to this formula, we know it's just C1 plus C2 plus C3, 100 plus 20 plus 400. It is important to note that your units are important. I know we talked about that already. Don't accidentally miss a unit here. That'll be a really they'll try and get you on that on the tests, I'm sure. In this case, 100 plus 20 plus 400 is just 520. Don't forget your units, microfarads. There you go. Hopefully that makes some sense. Okay, so power factor. So there's a couple different ways that we can talk about power factor and a couple different ways that we can solve it in different contexts. I'm not sure if I mentioned this before. The script is sort of going off the rails. Anytime I have DC, my power factor equals 100%. All of the current in a DC circuit gets consumed the same way. It doesn't push or pull the current away from the voltage because there's nowhere for it to go. DC is always, it's stagnant, it's steady. It can't move back or forth, right? The reason that we have power factor is because on an AC system, current and my voltage can have a phase angle shift, a difference between these 2 points. Generally, we talk about power factor in a percentage, and it is a percentage of the true power over the apparent power. Now, the units for those, true power is in watts or kilowatts or megawatts or whatever, and our units for apparent power are VA. Apparent power is how much power there would be if you just had a current meter and a voltage meter and you took a measurement of any circuit and I said, well, it's 120 volts and 10 amps, and I can tell you, well, this is 1,200 volt amps. That is my apparent power based on these 2 measurements. But unfortunately, that's only true if my power factor is 100%. That's only true if my current and my voltage are perfectly in phase. If there's no phase angle shift here, if I've got no if I've got no capacitive load and no inductive load pushing the current one way or the other in front of or behind the voltage, my apparent power equals my true power because my power factor would be 100%. Yeah, but that's not often the case. So if I give you an example where I've got my power factor, or we're solving for power factor, again, in percentage, and I give you, here's my example. I got my voltage is 160 volts current,
1 amp,
and I know my power is 120 watts. So how do I find the power factor for this system? Well, my power factor is my true power over my apparent power. In this case, it's going to be 120 watts over 160 times, then we're combining stuff, so the units get a little bit odd here, but my power factor equals 120 over 160, which means my power factor is 75%. Should be pretty easy to understand. Now, the other way to look at it, so again, with this example here, so if I were to plot these, I've got a voltage. Let me draw that in red here. My voltage, will draw that in red. This is going to be 60 volts at 0 degrees. And then I've got that is more like a 40-degree angle, but I want to make it easier to see. So this angle right here is going to be 15 degrees, given our example. So I know that my power equation is power equals volts times current times my power factor. Well, let's go ahead and start solving for that then. So my voltage is 60 volts. My current is 9 amps. And my power factor here, well, I know power factor just equals cosine theta. So we're going to solve for cosine of 15 degrees. Now, it is important when you're plugging stuff in on a calculator, especially if you're in scientific mode, there is an option to do it in radians or whatever grad is, or degrees. Make sure you're make sure you're in degrees unless you really know that you want to do stuff in radians. Degrees makes life a lot easier because it's kind of how we converse about things like that. So anyway, let's plug and chug this one. So 60 times 9 is 540. Well, 540 in this case is just my apparent power. That's my voltage times my current. So that is only my apparent power. I haven't factored in the power factor at all. So 540 VA. I still need to multiply that by my power factor, which is the cosine of 15. Now we can do this in two different steps. We need to find this right here, our power factor, and I expect our power factor is going to be fairly high because 15 degrees isn't that much of a change. So we'll type in 15. Again, make sure your calculator's in degrees. You'll get really confused if it's in radians. It's 15, and then we hit cosine, so it's cosine 15, 96.6-ish% power factor. Multiply that by 540 VA. So my total power is 521.6 watts, given this example here. All right, hope that made sense for everybody. Power factor is a kind of complicated thing, and I could spend a whole video just talking about power factor and the different equations for it. But if you understand this, that power factor is the cosine of this angle right here, and that it is also true that it is the proportion of true power over power factor, you should be good to go for your test. One of the last things that I want to talk about is transformer, full load amps, and short circuit current. So what I'm going to give you is a nameplate. The amount of energy a transformer can produce, the amount of current on the low side, is sort of independent of whether it's a capacitive load, a reactive load, or a resistive load. So it's generally given in kVA, in apparent power. We're going to have a voltage rating. In this case, it'll be 15 kV, 15,000 volts on the high side, to 480 to 77 on the low side. And then somewhere on the nameplate, it's also going to have a impedance, a percentage impedance. This is the nameplate information that we're given, and I need to find out both the full load amps and the short circuit current. Now, the formula for full load amps, kVA per phase. Sometimes it'll be in VA. So this will be our VA divided by 3 times the secondary voltage. So now why do we divide it by 3? Well, assuming it's a 3-phase transformer, we need to get it down to the number of phases that we're actually looking at, because we get the full load amps per phase. So in this example, we've got 1500 kVA, so that is 1,500,000 volt amps, and then we're going to divide that by 3 multiplied by our secondary voltage. Now our secondary voltage in this case I've got a phase to phase and a phase to neutral voltage. I want the phase to neutral voltage. So if you only had the phase to phase voltage, you would divide that by the square root of 3. So this is 277. So this would also equal 500,000 VA per phase. And then we divide that by the phase to phase voltage. And if I do that, that's 500,000 divided by 277. My full load amps, so the most that I could run this transformer, if we're running it at 100% load, the most I could run this transformer is 1,805 amps per phase. So that's how we solve for our full load amp. Under normal load, how much does the manufacturer say per this nameplate information? How much current can I draw all the time through a load, through a motor, through whatever it's powering? I can draw 1500 kVA or 1,805 amps per phase. That's how much I am permitted to pass through here. Now, what happens if I accidentally short X1 to XO? Well, I would have a short circuit current. And what is the magnitude of that short circuit current? Well, we've got another formula for that, which is short circuit current equals VA, the rated VA rating of the transformer from the nameplate, divided by our secondary current, VSEC. And again, this is phase to neutral, right? It's our line to neutral. That's our 277. VSEC multiplied by our percent impedance. So let's go ahead and plug and chug this real quick, just to run through it. So just as we did before, so our short circuit current in this case is our single phase VA, because we're going to do this per phase. I want my short circuit current per phase. So it's 500,000 VA divided by my secondary voltage per phase times my percent impedance, which again is 5%. So we're going to go 0.05. 500,000 divided by, put this in parentheses, 277 times 0.05. I get a grand total of 36,101 amps per phase. This is substantially more than our full load amps. So this is the amount that the full load amps is the amount that the manufacturer has designed the transformer to run for. Our short circuit current is the amount that would theoretically happen if I had a bolted short circuit fault, between XO and X1, right on the secondary stab of the transformer. That would be probably worst case scenario, but this is important because this is a number that we have to use when we're sizing things like fuses, sizing breakers, or most importantly for our line of work, this is the formula that we're going to use to make sure that we have the right size personal protective grounds when we're working on the low side of a transformer, whether we're at a substation, industrial facility, something like that. This is going to tell us what size grounds we have to hang in order to be safe working downstream. So really, really important stuff to keep in mind. Okay, last but not least, I want to make an honorable mention of something that I remember from one of my tests, and it's not that hard, but it definitely can throw you off. So if you're not familiar with a 4 to 20 milliamp transducer, essentially what it is, say I've got a power meter. Over here on this end of the scale is 0 watts, and say over here is 100 watts. So I can visually see what percentage of the full scale we're currently at right now. And then I'm going to have a transducer attached to that. Going to have a loop circuit that's going to go to something else, say a remote display. We're going to call it a display. It could be anything else. It could be a PLC. It could be a relay. It could be another meter. It could be some other process equipment that's dependent on this meter reading. So I know that this is supposed to have a 4 to 20 milliamp scale. It has some deadband. If it's below 4 milliamps, the display goes into error. Between 4 and 20 milliamps, it'll display the amount. And if it's above 20 milliamps, you got something wired wrong, and your display, again, is going to show you an angry error sign. So how do I know how much current should be here through the secondary transducer circuit? So if I say my scale, my full load, or my max of this scale is 100 watts, my current amount is 60 watts, how much current is going to be going through our 4 to 20 milliamp loop right now when we're at 60 watts. So the way that you would solve this for this sort of thing, so our milliamp output equals the percentage of the scale times 16. 16 is the difference between 4 and 20 times 16 plus 4 milliamps, because that's the bottom end of our deadband. So our percentage, 60, we're currently at 60 watts over 100 watts. It could be any unit, it could be any scale. We're going to do that times 16 plus 4. In this case, this one's pretty easy. This is 60%, so 16 times 0.6 is 60%. 9.6 milliamps of the amount of usable scale that we have, plus our deadband, plus our offset of 4. That means at 60% of scale on our meter, we've got 13.6 milliamps going through our transducer circuit. If you get a similar sort of question, hopefully that'll just ring a bell and make it a little bit easier for you to solve.
I'm back outside. Make sure you're subscribed and check out my other tutorials. Stay safe, and I'll see you on the next one. Thanks, guys.